Hey there, astronomy students. This is Miss Ruark. This is podcast 9.1. We're going to start talking about stars and all their characteristics, which will lead us into the evolution of a star and the death of a star in the next coming chapters. So, all right, let's talk about distance and brightness of stars. There we go. All right, so distances to stars. One of the ways that they can measure the distance to a star is by using it's based on this right here, which is a surveyor's method. Okay, so if you've ever seen surveyors, they're out, they put down two stakes, which would be this stake and this stake here. You can't see that point, but it's off to the side, right? Right here, and then this one here. Okay, and then across the way, they would find a landmark or an object to focus on. Okay, so here between the two stakes that they put, they would measure that distance, and that distance is called the baseline. And then they would focus in on the object across the way, and they would determine the angles. The angles here, the angles here. Okay, they would determine those angles and use those angles to find the distance, which would be this line here, D. No, sorry, I'm not using my mouse, so it's kind of crooked. Okay, there we go. To use to measure the distance, and the more distant the object is, or the further the object is away from the baseline, you're going to need a longer baseline, or the longer the baseline you'll need. Okay, well, astronomers will use a thing called the trigonometric parallax, which is pretty much the same thing, right? So the star, what you'll do is they'll take a picture of a star. Okay, they'll use the baseline that they're going to use for the bottom of the triangle is going to be the diameter of the Earth's orbit. Okay. Excuse me. They'll take a picture of the star that's nearby. They'll wait 6 months until it's on the other side of the sun, and they'll take another picture of it. Okay, and this would give us a total distance of 2 astronomical units, which would be the diameter of the baseline. And the distance, or the difference of the position of the star that they're looking at. So notice here, the photo taken is different. The distance, or the difference between the two, would be the parallax, or the apparent shift in position. Okay. The further out the object is, the smaller the parallax will be. Excuse me. And parallax is going to be expressed in seconds of arc. Okay. Well, ground-based, let's see. That's just what that talks about. Okay, so ground-based, the further away the star is, the smaller the parallax. Yeah, should be paying attention to what's in my podcast, right? Okay, so ground-based telescopes can't measure anything that's smaller than 1 arc second. Okay, and the reason for that is because of the atmosphere. It distorts, it blurs those stars. Okay, so here's an example of a way that they would use the trigonometric parallax to measure a star. So the nearest star is Alpha Centauri. It has a parallax of 0.76 arc seconds. Okay, and so how do they find that? Well, they take D is equal to 1 over P. D is the distance, P is the parallax. And they put 1 over 0.76, which gives us 1.3 parsecs. Okay, well, let's put that into something that's a little bit more feasible, a little bit easier to understand, because we know parsecs is a really big distance. So we change that into light years, and it would be the same thing as 4.3 light years. Okay, ground-based telescopes, oops, I said 1. That's supposed to be 0.02 arc seconds, sorry. So the distance would be less than or equal to 50 parsecs. Okay, I can't go any further than that because, well, the atmosphere distorts it. Makes it hard to see. Here we go. All right, proper motion. So with proper motion, all the stars, including the sun, are going to move along an orbit around the universe. Okay? And if we take photos of the same portion of the sky 10 years or more apart, it shows the proper motion of the stars. A proper motion of stars is just how they move and change throughout the years. Okay, so Vega has a proper motion of about 0.327 seconds of arc per year, where Rigel has a proper motion of 0.02 seconds of arc per year. They both have the same brightness and temperature, but Rigel has a smaller motion. Okay, so the smaller proper motion results from moving almost directly toward or away from you, or it could mean that the object is quite far away. Okay, a larger proper motion is going to result from a star being closer to you. Okay, so Vega has a proper motion of 0.327 seconds of arc per year, and Rigel has a proper motion of 0.002 seconds of arc per year. So we would assume that because Vega has a larger proper motion, that it's closer to us. Right? Okay. And this right here just shows the proper motion of stars in the Big Dipper and how they have shifted over the years. So 100,000 years ago, this is what the Big Dipper looked like. And see, they've shifted, and this one's come down. So now, this is what the Big Dipper looks like. And they're saying 100,000 years from now, it should be distorted to look like that. All right, so intrinsic brightness or absolute magnitude. All right. So the faintest stars you see with the naked eye are going to be around 6 magnitude. And the brightest stars have a lower number. For example, Sirius is a negative 1.47. The apparent magnitude, which we dealt with in first semester, tells us how bright the star appears. When we look up into the sky, the apparent magnitude is how bright that star looks when it's in the sky from us. Okay. The intrinsic brightness is going to tell us the total amount of light given off by a star. Intrinsic brightness or absolute absolute magnitude. Okay. So intrinsic brightness tells us the total amount of light given off by the star. It takes into account all the wavelengths. And the more distant the light source is, the fainter it appears. So think about it. If we have this bicyclist right here standing close to us, okay, we're here observing the bicycle. The light's going to be extremely bright. But what if we were to take this guy and move him back here? Well, it wouldn't look bright at all, right? It wouldn't look bright at all because this light is being scattered out along so much more of a surface. Okay, same thing with the truck here. Okay, so brightness and how it's related to distance. So brightness is related to a thing called flux. Okay. The more flux you have entering the eye, the brighter the appearance is. Okay. So flux, and this just gives you a way to look at it quantitatively. So flux received from the light is proportional excuse me, to the luminosity of it and inversely proportional to the square of the distance, which means if you increase the distance, you decrease the flux. All right. If you increase the distance, if you decrease the distance, you increase the flux, or the amount of light you're seeing. Let's see what else we got on here. All right, so for example, here we have star A, star B, and the Earth. Okay, both stars may appear to be equally bright, just as we saw with Vega and Rigel. Okay, they have the same brightness and the same temperature, right? They both seem just as bright, but one of them is going to be intrinsically brighter than the other because it's creating more of all wavelengths. Okay, so the one that's further away, which would be Rigel, is going to be intrinsically brighter than the star than Vega. Okay. And then Betelgeuse and Rigel also from the Orion constellation. Okay, Betelgeuse has an apparent magnitude of 0.41 and Rigel has an apparent magnitude of 0.14. Okay. Rigel is a blue star, Betelgeuse is a red star. So Rigel is going to be higher in temperature, it's hotter, and Betelgeuse is lower in temperature and it's cooler, right? And this just shows you the intensity ratio. It's saying that for every magnitude difference that a star has compared to another star, you're going to increase the intensity by 2.512. Okay, so if there's an intensity difference here of 2, or excuse me, a magnitude difference of 2, then the star would be 6.31 brighter or fainter. Okay, so here you have an apparent magnitude of 0.41 and an apparent magnitude of 0.14. Okay, well the difference between those two would be 0.27. So we would take this number here, and if you remember, this is a number we used a lot in the first semester when we did apparent magnitude. Okay, and we would raise 2.512 to that difference, which gives you a 1.28. So that's the intensity ratio, which means that Rigel is 1.28 times more intense than Betelgeuse. Right? How come it's more intense than Betelgeuse? Because it has the lower number. Remember, the bigger the number, the less intense it is, the less apparent, the less bright it is. Rigel appears 1.28 times brighter than Betelgeuse, but Rigel is 1.6 times further away than Betelgeuse. Okay, so that means that it is intrinsically brighter by 3.3 times than Betelgeuse. Okay, because it's further away, it's giving off more total wavelengths than Betelgeuse is. And let's see, what else did I not cover? So inverse square relation says that flux is inversely proportional to the distance covered. So the further the object away it is, the more light is scattered, and so it seems less bright. Okay. Now that would be if they were both at the same intensity, if they're both giving off the same amount of energy total. Okay, now they aren't giving the same amount of energy total because Betelgeuse is actually closer and Rigel is further away. So if we took two of them that had the same intensity but different distances, we would be able to compare them. All right, absolute magnitude. So absolute visual magnitude, or absolute magnitude, is the apparent visual magnitude of a star that's 10 parsecs away. And this just gives us a standard to compare these by. Okay, so it's the magnitude of a star that it would have if it were at a distance of 10 parsecs. Okay, so apparent magnitude is what we see. Absolute magnitude is this magnitude that it would have if it were 10 parsecs away. Okay, so what else do we have? Intrinsically brightest stars can be -8, and the faintest stars can be up to a +19. Okay, our sun itself is at a 4.78 for absolute visual magnitude, which means if it was 10 parsecs away, it wouldn't be that bright. It really wouldn't be that bright. Okay, so looking at our example of Betelgeuse and Rigel. Excuse me, I've got a bunch of junk in my throat. All right, if we were to look at Betelgeuse and Rigel, okay, Betelgeuse we said was 0.41 and Rigel was 0.14 for the apparent magnitude, which gives them an absolute magnitude of -5.5 and -6.8, which means that Rigel, look here, is still brighter. All right, so we can use that to determine the distance that they are away. So we would say that Betelgeuse is 152 parsecs away and Rigel is 244 parsecs away. Okay, and that's all they're doing with this, is they're using it to figure out the distance. They're using it to figure out the magnitudes and how bright they are. The distance module, okay, so if we wanted to calculate MV, we would use this right here. Whoops, I didn't circle it very well. Okay, the magnitude distance formula, and MV minus MV is the magnitude difference or the distance module used to measure how far away a star is. So what do we get from this? We know that the further away the star, the larger the distance module, the more distance the star is. Okay? I'm not going to make you do the calculations with this, but yeah. So the same thing it says right here, the further away the star is, or the larger the distance module, the more distant the star is. And that's all this is saying. It's just a bunch of numbers. You don't have to know all this. We're not calculating it. All right. Yep. Yep, don't worry about it. Okay, I thought this was pretty cool, and I'll see you in class.